Alright, the last thing we're going to look at here in this chapter is going to be the colloids. Colloids are not actually solutions, they're actually heterogeneous mixtures versus homogeneous mixtures. But this is kind of the best place they fit in. So here we go. What is a colloid? Colloids are solutions with suspended particles. So again, in essence, they're actually heterogeneous mixtures. So you got to be careful here. Okay, they are larger than what they are dissolved in, but you can actually see the difference. So they will look like solutions until you do the Tyndall effect. And the Tyndall effect is where they scatter light and you can then see the particles. So if you shine a light through what you think is a solution and you see the little particles in there, then that is actually a colloid and not a solution. You have to be careful. There are different types of colloids depending on what the phases are. Usually we talk about a liquid-liquid one, but it doesn't have to be. You can have a solid-solid, which are like alloys with metals, or you can have solid gas, or you can have all kinds of different things. You can have fog, whipped cream, shaving cream, aerosols, milk, mayonnaise, marshmallows. Those are all different types of colloids. Okay. When we talk about colloids, all right, we have hydrophilic and hydrophobic colloids. Water-loving colloids are hydrophilic. Water-hating colloids are hydrophobic. Okay. Now, in the human body, large biological molecules, such as proteins, are kept in suspension by an association with surrounding water molecules. And they fold up so that your hydrophobic groups are away from the water and inside the molecule, while the hydrophilic are on the surface. We have two hydrophobic particles. And in this case, then notice how the negatives are all kind of surrounding this because they don't actually absorb or dissolve into the water. Okay, so what we have is an adsorbed ion, meaning adsorbed, meaning it's just on the surface, versus absorbed, like a sponge absorbs something, it actually takes it in. Okay, here it's just on the surface, kind of like superficial-ish. Okay, what happens now is that typical hydrophilic groups are polar or charged. That would make sense because we're talking about water-loving, so you've got to be polar to like water. Okay, whereas hydrophobic colloids have to then be stabilized to stay in the water. Okay, and one way to stabilize the colloid is to adsorb, like we're talking about there, ions on their surface. And again, adsorption is when something sticks to the surface and actually gets taken inside of that particular substance. If ions are adsorbed onto the surface of a colloid, the colloid will appear hydrophilic when it's actually not. So it's how you get things that actually kind of like water, but not really. You get something to stick on the surface that likes water, and then the stuff on the inside never has to actually interact with the water. Okay. We're going to talk about a small drop of oil and water. Okay. If we add a small amount of sodium stearate to it, sodium stearate has long hydrophobic hydrocarbon, meaning HC, tails, and a small hydrophilic end. The hydrophobic tail is then absorbed into oil drop, leaving the hydrophilic head on the surface. So the hydrophilic end then interacts with the water and my oil drop is happy. So that's why water actually then stays in, that's why oil then actually stays in water, because you get something there to stabilize it, then the oil will actually kind of look like it's actually kind of dissolving. A soap acts in a similar fashion, whereas soaps are molecules with long hydrophobic ends and then hydrophilic small ends on the other one that then remove dirt by stabilizing the colloid in water. So you have the stearate, and then you have the long end that doesn't want it to be anywhere near water. So the end that doesn't want it anywhere near water gets absorbed into oil, and the part that likes water gets then kind of sticks out on the end and will then interact with the water.